Hello everyone, welcome to another concept section. Actually, you see these formulas in a lot of problems and wonder where to get them, right? So for instance, if you have two parallel plates and say you put a plus q on here and you put a minus q here and assume that this is infinite in extent, just assuming that they go forever, and separation distance is d and the area is a, and there is nothing between them, so these are parallel plate capacitors. So in this case you can actually show that your electric field is all just here. Electric field is between the plates, and electric field is 0 outside here, electric field is 0 outside here. So you ask, how much energy is this capacitor holding? Yeah, there are a couple of ways to tell it. So the energy in this whole thing, you can say, well, it's going to be if the voltage between them, voltage difference between them, delta V, let's not put 0 here, delta V is going to be, if the capacitance is C, then you can, so delta V is a couple of, if the electric field is E times D, this distance. So that's one would say it, and you can say using Q equal to CV. So another way to say that is 1 over C times Q. So if you look at the energy, you might say I took, say, positive charges from here, moved over there, and as you build it up, you can find the energy. So the energy is half times QV. This is Q, this is delta V. So you can write, using this Q equal to CV, you can write half CV square, and you can write half Q square over C. So this C here, that pen is start to, okay, so C is equal to epsilon naught, there's nothing between the plates, A over D. So how about the E? E here is sigma over epsilon naught. What is sigma? Sigma is Q over A. So this is, one can figure out the energy, and you can manipulate this whole thing. You can just say, okay, I got a whole bunch of different formulas. Can I write them in terms of the which looks like this? And answer is yes. You can say E is sigma over epsilon naught, and E is also, let's not like delta V, just write V over D. So sigma and V, and this sigma is Q over A times, so this is all related. So I have energy, take any of these formulas. So energy is, let's see, V, right, in terms of V square. Energy is half CV square. So let's write V in terms of E. So I have a half, you got a D square, E square, right? So let's write the C now using for parallel plate. So you can have half A epsilon naught over d square E square. So one other d cancels out, and A times d, this stuff is the volume between the plates. That's where the electric field is non-zero. So the energy is half epsilon naught E square times volume. So energy density is energy over volume is half epsilon naught E square. So that's the formula you get doing this way. But it's kind of hard to justify this completely. Okay, so how do I know that this is the energy? Here we looked at energy in building up the charges. So it looks like the energy is because the charges are separated. And here the energy doesn't, this formula doesn't really refer to charges, just the electric field. It doesn't say what the source of the electric field was. Over here, the source of the electric field are these separated charges. But in general, you can say I have a space here, and there's some electric field this way, and maybe over this electric field is that way, and electric field over here came in this space and get out like that, and maybe over here the electric field is that way. So this is some volume of a space, right? In that volume you have electric field at different places. So you can kind of look at a small volume, say you have let's call it d tau for the volume element. So in here you have some electric field magnitude. So electric field is a vector, so we can say electric field is electric field dot electric field is square root. So that quantity E, let's call that E0, just the magnitude. Okay, so it's at some point some distance r from some origin, right? And I want to integrate this, so I have E0, this will depend on where I am, E0 will depend on r, and I square it and multiply epsilon by 2, so that's density d tau, and then I integrate over this volume. So this will say amount of electric field energy in this volume. It's a very important formula actually, and it gets used in a lot of places. Okay, because it's density, you have a energy over volume as unit. You can derive this in much more advanced way, and I'm not going to do that here. Just want you to have a sense of how it's related to all the other things we have discussed over the course of this. Lots of videos covering electricity and magnetism. So this is an old thing, electrostatics. How about the magnetic field? How much energy is contained in the magnetic field? And it turns out the formula is this. Okay, and let's see if we can, in a simple situation just like over here, we're able to kind of get the formula from looking at a special case. We can look at a special case where we can do the algebra completely in a simpler setting. That's pretty good, right? So let's try to see where I can get this formula. Okay, to see this formula, what we're going to do, we're going to look at another circuit. Okay, so let's see. I have this circuit which has a kind of bypassing this, so it has a circuit like this, and this is infinite solenoid. So this is a infinite solenoid. So infinite solenoid. N turns per unit length. All this infinite solenoid, I'm going to say solenoid of length L. So this length is little l. N turns, the area of each of these turns, each loop, say A. So if you work it out, self-inductance L for this will be mu naught n square AL. So this you can work it out. I think this is correct. And if not, I'm going to find out that this is not correct in just a little while. Okay, just trying to go by the memory. So this is the resistor. So it's connected like this for a long time, and at t equal to 0, the current at this time is going at some I0, and I switch it like that. So you can say at t equal to 0, it was current was going that way, and suddenly the is going this way now. So this is circuit at t equal to 0, and you know this current will go and dissipate here, and eventually current will go to 0. So there is some energy somewhere, right, which is going to become heat over here. So that energy has no place to be except in the magnetic fields down here. So the magnetic fields were going up like this and going like this, going this. So magnetic fields are, so it's in the magnetic field here. So this will working out the energy lost over infinite amount of time. So energy dissipated should give me the how much energy is here. Energy dissipated in R from t equal to 0 to t equals to infinity. This must be energy that was stored in, there's nothing else, magnetic field inside solenoid. Okay, so that's my claim, and this makes sense from the energy conservation. Because how do I get that answer? So one way to do it is figure out how much the current at some time t, the current will be not I0, but it will be I0 e to the minus, because this RLC circuit we know R T over L. So this is, so formula for writing energy dissipation, working this out. The way we're going to work this out is going to be very simple. We're going to have a I square T, R I square T, 0 to infinity dt will be the total amount of energy. Use the letter W for energy. Okay, that will be dissipated. So this working this out is not that difficult in integral, because this is an exponential, and so it's going to be R times I0 square, and when you do this integral square, so L over 2R. You work this out, it's going to come out like that, right? This R cancels out, so we have I0 square half I0 square L, and at the t equal to 0, current is in solenoid is I0, right? That means magnetic field in the solenoid is mu naught n I0. That's the formula from the solenoid, which you probably have to remember or you have to derive it. So you can already see that this I can put for each I0 in terms of B0. B0 is the magnetic field, and if you don't like B0 is the initial magnetic field, right? That's magnetic field that was initially there. So half B0 square over mu 0 square n square, and then L, for L I wrote down the formula from before. You can always get this formula by doing what is L. The definition of L will be phi through solenoid equals to L L and the current through solenoid. So if you use this formula, then you get L. So phi through solenoid in the B0 is going to be B0 times area of each loop times number of loops. All right. So B0 A number of loops. So that's this is for each loop. So that's many area it has to go through. So that's the B dot dA. And then I can do B0 is just mu 0 n I0 equals Li. This I is I0, L cancel, and you can see L is n square mu 0 AL. So that's the formula. So I'm just going to go mu 0 n square AL. Okay, that's very nice. Only one of the mu 0 left. All of the n square cancelled out, and this is just the volume of this space inside, where the B is non-zero. B is 0 outside, right? Because of this assumption. So roughly what we got is half 1 over 2 B0 B0 squared times the volume. So now you can see that if I have magnetic field, it was magnetic field B0, but if in general some magnetic field B, a B square. So that's the formula for energy per unit volume in the magnetic field that's in the solenoid. However, it doesn't have to work only for solenoid. Just like we talked about electric field, we can imagine some other scenario. Okay, so we have a current carrying wire, and magnetic field is going around it, right? So these are the magnetic field lines going around it, and so we take some volume here. So this is a volume, and so you can see so B is different at these places, right? B is different these places, and you take a small box, and let's see it's at some location R with this origin I've chosen, and the box is, I'm going to volume, this is the volume element, the dx, dy, dz, for instance. So over here, what the B has B field, I'm going to take a magnitude of that. So I'm going to have a 2 mu naught B square at location R d tau, and I integrate over this volume. That will give me how much area, how much energy. This is how much energy is in that volume. So this is the energy in that volume. We can call it magnetic energy in that volume. Now you can put it together and you can say what's the total electromagnetic energy. So like a completely arbitrary place, some just say it's a box you're looking at. So there's some electric field. There will be some electric, maybe charges over there running or just static or whatever. So there will be some. So we can say, let's call that origin and some point r, and take a tiny box d tau. So I can say 1 over 2 epsilon naught E dot E for E square plus 1 over 2 mu naught B dot B, and these are at location R. This will be depends on where I'm in the box. Okay, and then d tau, there's the volume element, tiny volume element. If you integrate over this volume, you should get electromagnetic energy. Energy in the box. So this is how this gets used a lot, and I hope you kind of learned something fundamental definition wise. There is a much more involved way and much more mathematical way of seeing these formulas, which I haven't presented, but you can see in some advanced books. So I'm gonna kind of stop here, and maybe in the future we do some problems involving these formulas. Okay, take care, bye.